Thanks everybody for joining us today. My name is Abdullah Hussein. I'm going to be your coordinator today for Production Chemistry Roundtable. It's an event that is meant to bring together oil and gas professionals to talk about production chemistry stuff. It is a free knowledge sharing. If you want to introduce new technologies, this is up to you. Whether this is chemical, non-chemical, operational, or software technology. And it is free of charge to attend, to showcase, and to introduce your technology. As I said earlier, we are going to do this event every 3 to 4 months. If you have a new technology, whether this is chemical, non-chemical, or operational, feel free to reach out to us to maybe to give you a segment in the next one to show your technology. Our event today will include different segments. The first one, it will be myself and Bruce Horne. We will be talking about an introduction to oil and gas production chemistry. The second one will have Dr. Bård Kassa from Norway. He will be teaching us about mineral scale simulations in practice and introducing his scale prediction software, ScaleSim. And the third segment, we have Paul Stockwell. He will be talking about gas-liquid separations and focusing on the liquid carryover issues. And the last segment, we have Dr. Mark Peterman from the US. He will be introducing a real-time molecular analysis for H2S scavengers and biocides optimization. Please keep the chat out of your messages. If you have any questions, please put them in the question and answer section so we can go through them easily. So I'm going to go ahead and start the first segment. It is an introduction to oil and gas production chemistry. A quick introduction about myself. My name is Abdullah Hussein. I have been in the industry for 18 plus years, dealing with production chemistry stuff, including solids deposition, emulsions, and phase separation, corrosion problems, and also other production chemistry related issue. Here's a picture of a book I published 2 years ago. Check it out if you would like to. Also, I started a small platform called Chemdustry. We provide services in oil and gas upstream sector. Our services include training, consulting, and also fluids modeling. Regarding the topic that I'm going to talk about today, we have a training that is scheduled for April 20th to 24th. It is a 5-day training delivered online and covers most of the oil and gas flow assurance and production chemistry topics. If you are interested in that, please feel free to reach out to us. So the agenda for the first topic we're going to talk about is introducing the concept of the flow assurance, and then we'll see the origins of the production chemistry issues. And then I'll be talking about the 4 main types of solids, including scale, hydrates, paraffin, and asphaltenes. So this is the production system. What are we trying to do here? We're trying to extract the hydrocarbons from the first point of the system, the reservoir, and deliver them all the way to the surface, process the fluids, separate them, send the gas to the sales, send the oil to the refinery, and then process and treat the water and either re-inject it back into the reservoir or dispose off of it. While we're doing that, we normally get hit by one or more of these flow assurance and production chemistry issues, including scale, hydrate, wax, asphaltenes, microbes, reservoir souring, corrosion, sand production, and many, many other multi-phase flow issues. And here, when the flow assurance comes into play, because it's a strategy that assures the flow of the fluids from the first point of the system to the final terminals in an efficient, economic, and safe way. The core of the flow assurance is 2 basic things: the fluids physics, how the fluid flow in the system, and also the fluids chemistry, how the different phases react with each other. The flow assurance, as I mentioned, it is a discipline of science that has been developing over the years. So if we go back to the 1960s, or maybe a little bit earlier than that, to mid-1980s, it was a reactive strategy. So what it was doing basically is to avoid the problem. So you have hydrate, just inject methanol. If you have wax, inject an organic solvent, or maybe let them build up in the pipeline and then run a pig to clean the system from time to time. So there was no really solid strategy to manage these issues. And then starting from mid-1980s, going all the way to our modern time here, we have the predictive method of managing. Sorry, I'm just going to go ahead and mute everybody. So this is the predictive methodology, and in that one, because of the advances in the thermodynamic and the hydraulic studies that we have done, we developed models that can proactively tell us and predictively tell us what might go wrong in the system. So the strategy for that, we pull samples from the system, characterize the fluid, we do some thermal and hydraulic analysis, and then we do extra modeling for the fluid flow, for the production chemistry, to assess any potential risk in the system. And then we design our system based on that, and also design the mitigation. And then we apply the mitigation, monitor the system, and that normally goes in the shape of a continuous improvement loop. And we do that with every single production chemistry issue. So this is kind of like considered a full field management plan. And normally these studies are done at the earliest stages of the field development or at the feed stage. And to do that as well, we need a team to do that. People with different backgrounds, different specialties to do all of this predictive strategy of flow assurance. The new, approach of the flow assurance includes everything in the predictive strategy in here, and adding to that the recent advances in the digitalization, also in the new installations in the subsea and deep water systems, also the intelligent designs and operations, the AI tools that will be integrated in everything, and of course the decarbonization comes into the heart of all of that because of the policies that the government imposes on the industry right now. So this is just a quick overview of the flow assurance, the concept, and the timeline of its development. Now we're going to move to the production chemistry, where the production chemistry stuff are coming from. They're coming from the system itself, for sure. But why? It's because of the continuously changing parameters during production, and that can kind of like disturb the thermodynamic equilibrium between the different phases. And this triggers wide range of reactions between the different phases and components of the system. So let's take a quick look at these different phases and the different reactions that might show up during production. So if we take the gas phase, it might react with the water phase at low temperature, high pressure to give us gas hydrates. The oil phase, it has many reactions. So it can drop asphaltenes because of pressure drop, because of reaction with another type of crude, or reaction with injected gas like CO2 gas or gas lift. The oil can also drop waxes if the temperature fell below a certain limit. The oil can also react with the water if there is enough emulsifying agents to give you emulsion. The oil can also react with the water under certain pH to give you soap, either soap scale or soap emulsion. Another phase, the produced water. Different waters can react with each other if they are incompatible to give you scale, or the water can be called self-scaling by itself if the changes in the pressure, temperature, and pH induce scale deposition. Another phase, the treatment chemicals. We inject them to manage the issues in the system, but sometimes they can be incompatible, or we might overdose or underdose them, and these can trigger either corrosion or deposition issues in the system. Another phase, the reservoir rocks. These can react with the different phases in the system and induce either sand production, fines migration, clay swelling, and many other, formation damage issues. Another phase, the metallic structures, the pipelines, the vessels, the tubing. These can react with the different fluids, and the ultimate result will be corrosion and system integrity issues. The last one, we have the microorganisms. These live in the system, and they hoard and scavenge their nutrients, and they will cause microbial corrosion or biomineralization. So these are the phases that we have, and these are the challenges that might show up because of that different reactions, whether these reactions are chemical, electrochemical, biochemical, or physical reactions. And sometimes it can even get worse, because a problem can induce another problem. Corrosion can induce scale. Scale can induce corrosion. Bacteria can induce both of these, scale and corrosion. And it can get even worse, because sometimes we inject chemicals for treatment, like corrosion inhibitors. We inject these to mitigate the corrosion, but sometimes they have surfactancy in them, so they can actually stabilize emulsions for you. So if you look at the production chemistry issues, they look like a very compact interconnected network. So if you are someone that is dealing with these issues, you have to have a plan to manage all of that. The first thing is to map and define the phases. The second thing is to map and define the issues. The third is to prioritize which problem you should solve first, because it might induce another problem. And then the last thing is to make sure that the mitigations that you normally do are actually compatible. They're not going to cause any side effect issues for you. All right, normally the management of these production chemistry issues, they take the loop that we mentioned earlier. You study the system, you study the fluids, their characteristics, and then you do the risk assessment, design the mitigation, and then you monitor the system after applying the mitigation, and optimize and improve after that. So that was just a quick introduction to the production chemistry issues. Now we're going to move right quick to the solids that normally form in oil and gas systems. And as you can see, there is huge amounts of solids, and I'm not including everything in here as well. Where these solids can form, anywhere in the system. What are the impacts of these solids? Huge impacts that can cause literally millions, if not billions of dollars each year. The ultimate result for sure will be production decline, loss of revenue, expensive maintenance. They can also cause formation damage, flow restrictions and blockages. They can damage the different production equipment. They can induce environmental and safety issues. Some of these are actually hazardous materials, like the norm scale. This is a problem. Pyrophoric scale, this is an environmental problem. Also, the hydrate can be, a safety issue as well. These solids can also induce corrosion. They can sustain microbiological activities, because bacteria can live underneath them and thrive in a nice and cozy way, and they can even avoid the biocide treatments in that situation as well. The solids can also impact the chemical efficiency, because some of the chemicals can absorb on their surface, and then they kind of like consume some of the chemicals. Related to the second segment that Bruce is going to discuss with you guys, is the solids has huge impact on the phase separation. First, they stabilize the emulsions, like you see here, different kind of emulsifying agents that stabilize the emulsion. Secondly, they precipitate all over the separation vessel. They interfere with its operations. They also decrease or change the effective size, and in that way you are expecting to change the retention time, which is a very important parameter for the phase separation as well. And on top of that, as I mentioned earlier, some of the demulsifier can get absorbed on the solid particles, and this is going to consume some of the demulsifier. Now we're going to go right quick to the first type of solids, the mineral scales, and these are associated with the water handling or water producing systems. If you look at the water in oil and gas fields, they have heavy loads of ionic species. When these ionic species concentration exceed their solubility limit, or the parameters change, they will go through, the precipitation and the deposition steps, including these 5 basic steps: supersaturation, nucleation, crystal growth, adhesion, and the aging. What kind of types of scales we expect in oil and gas systems? We have carbonates, sulfate, sulfide, oxides, hydroxides, and chlorides. And that's not everything, because some of these will have polymorphs or phases. So you might end up with actually tens of these types of scales usually form in oil and gas systems. Some of them will have different characteristics, different features, different methods for mitigation as well, which makes the problem very complex. What are the factors impact the scale formation? The first thing is the ions concentration. If you look at these reaction mechanisms here that manage the way the scale are formed, they all depending on the ions concentration. The second thing is the Please keep your mic on mute because we don't want any interruptions. So the second factor we're talking about here is the mixing of incompatible waters. So injection water with produced water, these, is a big source of scale formation. Any pressure change, temperature change, pH change, corrosion problems, microbiological activities, geochemical reactions that might happen in the reservoir. Hydrodynamics of the system has a huge impact as well, specifically on where the scale is going to form. The production regime, the gas-liquid ratios, these also have a huge impact on the scale formation. And lastly, we have the fluids composition change. Any change in the water salinity, it might trigger some scale formation. Any chemicals added, like methanol, H2S scavengers, these are very two common examples of chemicals we inject, and it might induce the scale formation. So the first step in managing the scale is to do a risk assessment. The first thing, you will pull some samples from the system and you analyze them. When you do that, you have to be careful, get the samples from the right spot, and also make sure that it is preserved. And then you run some modeling using the scale software, ScaleSim, as I mentioned in here. Sometimes we might need to do some experimental work, and then we study the factors that impact the scale formation as well. And sometimes we need to learn from analogy, from similar case studies. So we take all of that, put them all together in a risk matrix, and see how bad the problem is going to be. Based on that, we will design the mitigation either with chemical or non-chemical methods. The chemical, which is very, very common, include the scale inhibitors, which can be injected in a continuous basis or can be batched into the system in the form of scale inhibitor squeeze jobs it down into the reservoir. We can also use water shutoff chemicals to block the zones that are producing scale forming water, or we can use the scale dissolvers to dissolve the scale that already formed in the system. And each type of scale will require its own type of dissolver. The other type is the non-chemical methods, and these are can include the operational methods, which basically rely on the idea of avoiding scale formation by improving the system design, avoid mixing incompatible waters, using filters to remove sulfate from the system, or using the internal coating. There's also the physical methods, and these rely on the idea of prevent the scale particles accumulation. There's magnetic and there's also electromagnetic techniques. These are the two common types. There's also mechanical methods to remove the solids that already formed in the system. After you apply the mitigation, you have to monitor your system, and that can be done using many, many ways, either watching the system parameter, the pressure, the temperature, the productivity, the water cut, watch the water chemistry as well. So the ions concentration, the scale inhibitor concentration, you run the total suspended solids, which is a very effective method of monitoring the scale. Can be done in a simple way or in a little bit advanced way by taking the filters after you do the test, and you run some SEM analysis on them to see what kind of shape of crystals are there. Are they actively forming or already modified because of the chemical? You can also use the coupons, spools, side stream. These are really real-time effective methods to watch the scale formation, or using some sensors and the well logging data. Now we're going to move right quick to the gas hydrates, because I want to give Bruce some time to talk about the emulsification. So the hydrates are ice-like molecules. They normally form at low temperature and at high pressure. So when these conditions are sustainable, the water molecules in the system will try to form cages by the hydrogen bonding. And then whenever, if there is any hydrocarbons in there, specifically the low molecular weight, gas molecules, they will entrap inside these cages like you see in here. That might seem like a fancy and nice idea, but the outcome of it is very, very nasty, because you might end up with a plug like this, which sometimes, if you're trying to remove them from the system, they can rupture the pipeline and kill someone. And there's a lot of cases reported like that. Or if any of you guys heard about the Piper Alpha, gas hydrates was a part of the causes of why this catastrophe happened. Or the Deepwater Horizon. There's some recent studies that are saying the same thing. Gas hydrates might also play the role in the catastrophe of the Deepwater Horizon. How to assess the risk of the gas hydrates? The same thing. You pull samples, analyze them, and then you run some simulations. Here's the pipe sim for you if you want to do that. Whenever you do that, you will get a hydrate formation curve. This is how normally that looks like. It tells you the zones of hydrate formation. So if your production regime is going through this way, then you might have some hydrate formation in your journey from the reservoir to the surface. So you might need to, optimize your operations by injecting chemicals or using any of the mitigations that we will be talking about. But the core of that is you need this hydrate formation curve to assess the risk of the hydrate. You can also study the factors of the hydrate formation, the temperature profile of the system, the pressure profile of the system. Sometimes some surfactants can affect the hydrate formation as well. Sometimes we need to do some experimental work, like the rocking cell. This is a very well-known test that we use to study the hydrate formation in different systems. You can also learn from the different case studies and the system analogies as well. How to mitigate the hydrates? Similar to the scale, there's chemical and non-chemical methods. The chemical, we have three basic types. We have the thermodynamic inhibitors like methanol, glycol, salt, but these we inject them in a very high dosage. If you're looking for something with a little bit lower dose, then you have the kinetic inhibitors or the anti-agglomerant. For the non-chemical methods, we try to avoid the hydrate formation by managing the system temperature and pressure to avoid them going into the hydrate formation zone. As I mentioned earlier, that's why we need this curve, because it tells you the zone or the region where the hydrate is forming. So you need that curve to design your non-chemical methods. This can be operational by removing the water from the system, using the cold flow, by making the hydrate in the form of a slurry that can be manageably flow in the system, using some internal coating, pressure control, or improve the design. Most commonly is the use of the thermal methods, either with active heating or thermal insulation, to keep the system temperature above the hydrate formation temperature. And if the hydrate is already in there, we use mechanical methods such as pigging, coil tubing, or wireline to remove it. Most of the time, coil tubing will be your best friend, because it includes many, many features that can resolve the hydrate plug efficiently and very quickly as well. How to monitor the hydrate formation in the system. So you watch out the system pressure, temperature, productivity. There's a technique called the pressure pulse. You can use it as well to see if the system is forming hydrate or not. Watch the dew point, watch the gas composition, the water cut. If there is any significant change in the gas composition or the water cut, that means these might be ending up as hydrate somewhere in the system. There's also some sensors, pigging operations, and also run simulations to make sure that your system is not vulnerable for hydrate. Our third type of solids is the paraffins, and paraffins is a fraction of the crude oil. So we have the Sara fraction of the crude oil. The paraffins belong to the saturates fraction. They are high molecular weight alkanes. Their carbon distribution start maybe from C15, depending on the crude. So it can be C15, 18, so depending on the crude source. They start crystallizing at when the crude oil temperature falls below the wax appearance temperature. So you need, if you want to look at the formation mechanism of the waxes, the first thing is the fluid cooling, which can be done either using fluid mixing whenever you inject anything in the system that cools it down, like during the fracking, during water injection, squeeze jobs. These can all induce wax deposition in the reservoir because of the fluids mixing. There's also the heat loss throughout the system. When the fluids are moving, there will be heat loss all over the system. There's also the Joule-Thomson cooling. And that's when, the systems that have gas in it, and then you'll pass through some restrictions. It's called the throttling effect. So that's the first thing, the cooling of the fluids. When that happens and the temperature falls below the wax appearance temperature, the wax molecules start building up and end up making the gel or the wax network. So this is the second step in here. After that, this wax gel will try to age or harden and get very solid by one or more of these mechanisms in here: molecular diffusion, shear dispersion, Brownian diffusion. Most of the time, molecular diffusion will be the main controlling mechanism. So what are the factors impact the wax deposition? So the system temperature. That's why you need to have a full system temperature profile, and you need to know the crude oil, wax appearance temperature, and pour point, because these will tell you where the wax is going to start forming and how bad is it the flow is going to be after that. You also you need to know the system pressure profile as well, because the pressure drop can induce the wax deposition because of the Joule-Thomson cooling or because of the loss of the light ends. Also, the oil composition is very important, and the system hydrodynamics. How to assess the risk of the waxes? Again, you pull some samples, you analyze it. Normally we run this list of analysis, and then we run some simulations. Again, you have pipe sim to do that. The outcome of the pipe sim will tell you the wax deposition envelope. It tells you, where the waxes are expected to form in the system. Based on that, you will do your, activities to prevent that. Sometimes we might need to do some deposition experiments as well, like cold finger, flow loop, to simulate the system. Also, we study the impacting factors and look at the case histories and learn from them. You take all of that, combine them all into a risk matrix, and then you start mitigating your waxes. What are the wax mitigation methods? So we have the chemical and non-chemical. The chemical, we have a wide range of chemicals actually for the waxes. We have the paraffin inhibitors, pour point depressant, wax dispersant, and also we have the paraffin solvents as well. Each one of these have a specific way of applying them. For example, paraffin inhibitors, we apply them upstream of the wax appearance temperature. Pour point depressant, we apply them upstream of the pour point of the crude oil. If you're going to look at the non-chemical methods, so we have operational, thermal, and mechanical methods. So the operational is you try to avoid the wax deposition in the system. There's cold flow, very similar to the cold flow we mentioned in the gas hydrates. You basically induce controlled way of forming wax slurry that can, easily flow in the system. There's also the internal coating, the pressure control, and improving the design as well. Thermal methods, very similar to the gas hydrates. So you basically add heat or insulate the system to keep the system temperature above the wax appearance temperature or above the pour point in very severe cases. The mechanical methods, we have the pigging, the coil tubing, and also we have the wire line. How to monitor the system for the waxes. So you watch the production data, the pressure, the temperature, the rates. You do some samples and you run some lab tests, viscosity, wax appearance temperature, pour point. You check the crude composition from time to time. You check the coupons. You check using the sensors, pigging data, the well logging, all of that stuff to monitor for the waxes. The last thing we're going to talk about today is the asphaltenes. This is another fraction of the crude oil. It is the heaviest fraction of the crude oil. That's why we call it the cholesterol of oil, because it can deposit in the system like how the cholesterol deposit in the, the blood vessels in the human body. They are the heaviest fraction, also the most polar fraction as well. and it's the one that gives the crude its dark color. If you look at the structure of asphaltenes, we have two basic structures. The continental, this is where the aromatic core is in the middle of it, and then you have side chains coming out of it. And there's also the rosary structure. This is when you have a little bit of little cores here and there, and they are interconnected with side chains. If you want to define the asphaltenes in another way, they are the alkane insolubles of the crude, but they are soluble in the toluene. How they deposit in the system? They deposit in a hierarchical way. So starting with the molecule, that is normally stable under reservoir conditions. But when the system, condition change, like a change in the pressure drop, temperature change because of pH or acidizing, mixing incompatible crudes, gas lift operations, CO2 injection, any change in the crude oil composition because of the shear and the system hydrodynamics. Even the streaming potential in the system and the corrosion can induce destabilization for the asphaltenes. When that happens, they will start to aggregate. So they will form nano aggregates, and these nano aggregates will keep increasing in size, and they keep clustering up to form a cluster. And these clusters will keep growing in size into flocculates, primary particles, and then micro aggregates, and then eventually the hard deposition that we normally see in oil and gas systems. How to assess the risk of asphaltenes? The same thing. We pull the samples from the system, make sure they are pressurized, conditioned at the system temperature as well. And we run analysis, SARA analysis, PVT analysis, and many other analysis, as you see in this list in here. Well, we also can run some crude oil instability analysis specifically done for the asphaltenes, as you see in here. And then after you finish all of that, you run some simulations. Again, you have the pipe sim to do that for you. And the outcome from that will be the asphaltene deposition envelope. It tells you the region where the asphaltene is basically going to deposit in the system. Sometimes we might need to run some experiments. There's a lot of experimentation on the asphaltene deposition. Most of the time they're done using, alkane as a precipitant. And then you study the system, other systems and analogy, learn from these lessons. And then you will build your own risk matrix. Based on that, you will start to design the mitigation. Mitigation can be chemical or non-chemical, very similar to the other stuff. The chemical, we have asphaltene inhibitors, asphaltene dispersants, and we also have the solvents, which most of the time should be aromatic solvents. Coming to the non-chemical methods, we have operational. We try to manage the system to avoid the asphaltene instability. The problem with the asphaltene is we know a lot about the chemistry, but we don't know all the information about the behavior. We know about the structure, the molecular weight, and many things, even the function groups, but how these function groups and how these chemistry actually react in a complex system like oil and gas that includes gas, oil, water, rocks, all of that. This is the hard part when it comes to the managing of the asphaltenes. So as I said, you can use operational methods, improve the design, avoid mixing incompatible crudes, internal coding, pressure control. One of the things that normally done in systems that use gas lift is to improve the gas lift operations. There's also some physical techniques like magnetic or ultrasonic. And lastly, we can use mechanical techniques to remove the already formed asphaltene deposition. Last thing before I hand it over to Bruce here is the continuous monitoring of the asphaltenes. So how to do that? You watch the system production data, the pressure, the temperature, the productivity, production rates. You pull samples, run some lab tests. You also watch the coupons, any sensors, the pigging data, and also the well logging. So that's everything from my side. I think I went a little bit overboard with the presenting, but I'm just going to give it here to Bruce. Are you here, Bruce?
I am here.
Okay, so sorry if I'm a little bit, I went a little bit too far. I'm just going to hand it over to you. Just before we go, a quick introduction about Bruce's background. Bruce is an industry recognized and respected subject matter expert in oil and gas industry with specialization in demulsification and water clarification. He has over 29 years of experience. He was employed in Champion for over 8 years and Baker Hughes for over 15 years. When he was in Baker Hughes, he was the global SME for demulsification and water clarification. Currently, he is working for a leading surfactant manufacturing company. He's leading their demulsifier technology. He has a track record of managing domestic and international projects for super majors in the world. He has managed multi-million dollars projects from initiation to commercialization for Shell BP in North America, Nox in Latin America, ExxonMobil in Africa, Chevron and Aramco in the Middle East, and ConocoPhillips in Europe. I think I'll hand it over to you, Bruce.
Okay, do I have control of the slides?
No, I'll take care of it from here.
Okay. So we're going to talk about demulsification, and that's oil and water separation, which is incredibly important because you can't sell the oil unless you have the BS&W or the water content down to a certain point. It varies in most places, but it's usually 0.5 in most areas. Anyway, there's no place to store thousands and millions of barrels of water per day, so you have to get the water out so you can sell that oil. An emulsion, to be very basic, is a dispersion of two or more immiscible liquids. So it's two or more liquids that don't usually mix. The dispersed phase is known as the internal phase, and the continuous phase is known as the external phase. So most of the emulsions that you see out there are water and oil emulsions, where oil is the external or continuous phase, and there's tiny droplets of water dispersed throughout, and those are the internal phase. Okay. Go ahead. Next. For an emulsion to form, you have to have the two phases, and in our case, it's oil and water. You have to have a emulsifying agent, something that stabilizes the water and keep it from coagulating and falling out. These emulsifying agents are surfactants that keep the water from coming together. And then you have to have shear or agitation to mix these two fluids. Good, next slide. So there's many emulsifying agents, but some of the most common ones are minerals found throughout the reservoir, scale, corrosion scale, asphaltenes. Asphaltenes are probably the most abundant stabilizing agent out there. Wax, resins, organic acids, drilling fluids, because drilling fluids have emulsifier agents in them, and other treating chemicals, other production chemicals. Next slide. So there's a lot of factors that make emulsion formation happen or make it happen to a greater degree. Oil to water ratio, the more water there is, the less chance of having an incredibly stabilized emulsion. You will have emulsions, you just won't have as tough of emulsion as normal. And the more water there is, there's going to be some free water which will not stabilize. The size of the water droplets, the smaller the water droplets, the more dispersed, the harder they are to destabilize and bring back together. The temperature is almost always a factor. The hotter the fluids, the less viscous the fluids, and the easier that the water droplets can move about and come together. And of course, the emulsifying agents, sometimes there's just a handful of them, and sometimes there's literally dozens or hundreds of emulsifying agents. So if you have more emulsifying agents, the more difficult it is to find a right demulsifier to counteract all of them. Obviously, system turbulence is a big factor with the expansion joints, the pumping of the fluid from the reservoir, ESPs, gas lifts, such as that, and mix valves or pumping stations on the surface. And then fluid densities. The closer in density that the oil and water is, the harder for it is to separate. Normally, oil will float on top of water, and the water will fall to the bottom. But on the extremely heavy oils, such as the Alberta oil sands, the density of the oil is actually less than the water, and the water will float on top of the oil. Next slide. So there's three types of emulsion. The one that we see most often is the one that has water internal or water dispersed through the oil. Then you have the oil in water, which is the reverse emulsions. Those are normally treated with clarifier or clarifier-like products. And then you have the water in oil and water emulsions, which happen a lot in the SAG-D community, where you have a regular emulsion inside of water. So you have to break the first emulsion before you could go about and break the second emulsion. By this means, on this one particular, you'd have a clarifier or a reverse breaker, drop most of the free water, and then deal with the regular water in oil emulsion after that. Next slide. So this is just a nice illustration to show you what the demulsifier does. You have two water droplets surrounded by stabilizing agents, and these stabilizing agents will keep the droplets from coming together and making larger droplets. And that's basically the only thing that happens is you make larger and larger droplets until the gravity pulls them down and they fall to the bottom. But in this illustration, you see the stabilizing agents preventing the droplets from coming together, but then the demulsifier or emulsion breaker comes in and disperses the stabilizing agents so that the droplets can coalesce and become larger. Next slide. So there's multiple things that come into play in demulsification. It's mechanical, which is your heater treaters, your free water knockouts, and your other vessels. Thermal, which is heat. Electrical, which isn't available all places, but in downstream in the refineries, almost every refinery has electrostatic coalescer or desalter. This electricity are grids that run throughout the heater treater and help you remove the last of the free water. Chemical, of course, is the demulsifier. Without the chemical and the mechanical, you can't have it coalesce and separate the two phases. You have to have multiple things to take care of most emulsions. There's some other less common factors that we will talk about in some of the classes that we offer. Next slide. So the mechanical part are the phase separators or the treaters, heater treaters. And the two major versions of the heater treater are the horizontal and the vertical. They both have their ups and downs. The horizontal, I believe, has a better separation ability because the interface is spread out and larger, whereas the vertical ones are more suited to places that have a very small footprint, like an offshore facility where there's only so much area that you could put your separation vessels and the other mechanicals that are present offshore, such as your generators and your gas compressors. Next slide, please. Here is a free water knockout. Now, every system is different. Some have free water knockouts, some have heater treaters, some have both, some have hydrostatic separators. There's multiple versions of the same equipment or of different equipment, but the two most commons, of course, is the heater treater number one and the free water knockout. The free water knockout is just what it says. It lets go of the free water that's not stabilized so that the chemical can focus on the stabilized emulsion. And this is where the bulk water is dropped out and then removed from the continuous phase of oil. Heater treaters are very, very common. Most places have at least one, if not more. And there's multiple mechanical issues or mechanical parts to that. the weirs, the separation of the clean water and the clean oil, the heat, of course, and how it's flowing into the vessel so that it spreads and washes out water. The heater treater, of course, is very much like an electrostatic coalescer. It's just the electrostatic coalescer usually has 3 grids where high voltage electricity is put into the fluid that helps excite the droplets of water and coalesce them quickly. But the electrostatic coalescer only works on the last phases and only on 10% water or less, because if you have too much water flow over to the coalescer, it'll short out the grids. Next slide. There's also wash tanks, and these are happening in very heavy crude productions. So they just basically sit and let the coalescence happen. But the oil comes into the bottom and it goes through the water, and that water helps wash out the emulsified water and the free water that is entrained within that oil. And then slop oil tanks are tanks that have water content higher than the pipeline specification, that have BS&W over usually 0.5 or whatever the spec is. Those are normally treated with a slop oil chemistry or a slugging compound. Next slide. So here's an illustration. You have your oiled in water emulsion. You add your reverse emulsifier. The oil's droplets are neutralized from positive and negative charges, and they become larger and larger. At this point, they start becoming very large, so that the flotation and the density differential between oil and water floats the oil to the top. The same exact principle happens in the normal emulsion, where the water is the dispersed phase. Your demulsifier destabilizes the agents that are keeping them in solution, and then the droplets can come together and form larger and larger volumes, and then they're heavy enough to fall out because of the gravity differential between the oil and water. Next slide, please. Some of the most common demulsifier chemistries out there are listed here. The absolute most common chemistry is the alkyl phenol resin. Probably most demulsifiers out there have at least 50 to 80% resin, and resins are used probably 80 to 85% of all demulsifiers in the world. Those drop water and are primarily known as water droppers, but they also do other treatments in different crudes. So you have to test them to find out exactly what they'll do. But they do drop water primarily. They could also do dehydration and interface control, but they're known as water droppers. The polyol block copolymers are just large strands of repeating units that help flock the water droplets to the surface and also help coalesce the water droplets together. The high molecular weight cross-link polymers are very good at dehydration, and they're probably the second or third most used demulsifier chemistry out there. The high molecular weight cross-link ester are very good for dehydration as well. So these two chemistries take the last drops and help bring them together, whereas the resin drop the bulk water, these take the last of the water droplets and help bring them together, because there's probably just a few droplets dispersed, but it still takes your oil above the BS&W. And I forgot to tell you that polyol block copolymers are very good for interfacial problems, handling the interface and helping those collapse and cause less issues in the interface. Amine polyols are not as common, but they're used, and there's a few other chemistries out there like the imines and things like that. All of these chemistries, except the sulfonates and sulfates, have ethylene and propylene oxide on them to give them water solubility and oil solubility at the same time, so they can go to the water droplet but still exist in the oil phase. The sulfonates and the sulfates are slop oil chemistries and sluggers. They're used in everyday chemistries, but they help with the slugging. That's why they call them sluggers, of the emulsion down to the bottom, so that can be resolved by the other chemistries. Next slide, please. So to select a demulsifier for a problem or a new field, you need to do a field survey and find out the objectives. You need to know how the system works and what the system is made of, the retention time of the different vessels, the agitation rates, and how the fluids move, if they're laminar or turbulent. There's calculations you do for retention rates and agitation times. Then you look at the risk assessment of the whole situation. How difficult is it going to be to get your chemical to work? I mean, is there a lot of retention time or not much retention time? Is there plenty of heat or not much heat at all? There's different risks that make the demulsification either easier or harder. Then, of course, you have your bottle testing, and that's your ability to find the correct demulsifier blend that you will pump at the end and deal with the emulsion in most situations. Being that most situations being you'll have additional oil, you'll have larger water cuts, you'll have backside treatments of corrosion and other things. So your chemical needs to overcome other factors that happen throughout the field. Then you have a field trial to test the chemical you picked while you're bottle testing. Now, when you bottle test, you need it to match the field as closely as possible, but it won't match the field perfectly, but you need to match it close. In the field trial, you're actually putting the chemical into the system to see how it will actually work in the real world. And then after the field trial, or at the end of the field trial, you start optimizing either up or down on the dosage rate, or maybe the chemical location injection point, so that you can optimize and make it work to the best possible degree it can. And then if you're in a large field, you're probably only working on one train. So at that point, you're going to add your chemicals to the next train and the other trains after that to see if you can get the entire field treatment. Now, some fields are only one or two wells, so that doesn't apply. But we're talking about the huge fields in Kazakhstan, Russia, Saudi Arabia, where there's multiple wells going into different systems. Next slide.
So we're probably gonna take 5 extra minutes to finish that. My apologies, it's all my fault because I didn't start the event earlier. I just started like 10 minutes later. So we probably will try to finish the this segment in the next 5 minutes, and then we'll move right away with Dr. Board with the next segment.
So general
Yeah,
bottle.
go ahead.
Oh, go ahead, Abdullah. Are you done?
Yeah, go ahead.
So the general bottle test is fairly complex if you don't know what you're doing in the field survey. But once you get the field survey information and you're getting enough experience, you can set up the bottle test. You put your emulsified crude into a bottle or a tube. You add your chemical to that bottle that you're testing. And of course, you're doing multiple bottles at once. You're testing multiple chemicals. You have your heat and agitation present, so you shake up the bottles with or without heat, depending on the heat of the system. And then you watch the water coalesce and drop out, and you read your water drop over certain periods of time. during a slow period where the bottle is not moved. After the retention time is met in the bottles that is the same as in the field, you'll take a small aliquot or thief of the oil at a certain level. That level is usually 20 mils or 15 mils above the interface, that where the oil and water meets. You'll take 20 mils above that highest one. So you have 30 bottles and you get 20, 50, 30, 20, 20, 8, 3, 5. So you have 50. So you thief them all at 70. That's your basic bottle test. We, of course, teach that in much more details in some of the courses we offer later on. Next slide, please. Go back one more. Okay, so you need to have the right equipment, a centrifuge, a water bath, syringes to micro syringes to add your chemical and ppm dosages, cannula and syringes to thief the oil, and there's other centrifuge tubes and things like that. There are, of course, basics that you're going to use a centrifuge, but there's other tools out there that we can discuss in more detail, like I said, in our other classes. You make sure you have the sample of your emulsion done in the right location so you get a commingling of all the crude that's being treated in a system. And you also need to use your crude very quickly, because if you don't use it and it's not fresh, the second you take it off the system, it starts to oxidize and change. Then, like I said earlier, you need to mimic the system as closely as possible. It can't be perfect, but you have to get enough experience to do the things that need to be done in the bottle test versus the real system. The basic procedure I went through just now, but it's a little more complex than that. And then you look at your results, and from your results, you decide your best option of your demulsifier. There might be one or two options or three or four, and then you choose your winner. You choose your winner depending on availability, price, treatment, and ease of handling. Next slide, please. Field application. There's multiple places that you can inject, but most people want to inject it as far upstream as possible so it gets dispersed into the crude, so it gets to the droplets. A lot of people want to inject it at the header because all the chemical can be injected in one place, and all the crude oil comes together at that header, so that chemical can disperse into the entire field of crude. Then some people inject it at the free water knockout just prior to the bulk water drop, because it's easy to do, and at that point most of the crude's together. And then there's injection points upstream of three-phase or two-phase separator. It just depends on the field and the dynamics of what you're seeing on where you inject the chemical, but most of the time you want it as far upstream as possible. Next slide, please. Troubleshooting. If there's a problem in the field that your company has, you ask and try to find out if there's any system changes, like new wells, or they've sent some wells off into test separators, or there's increased water production, or increased solids production, or a batch treatment of corrosion inhibitor. Multiple things can happen to change the dynamics of a field and its system. Maintenance, intervention, scale squeezes, so many things, hot oiling of paraffin, chemical delivery. Is it the right chemical? Is the chemical off spec? Injection skids working? Are they not working? Are they plugged? Is the chemical empty? Is the pump actually working? Or is it choked off? And then solids. Sand, silt, clay, organic acids, naphthalenes. There's multiple solids that can cause issues. Acid as a demulsifier is not normal, but it is used sometimes because demulsifiers, not always, but sometimes work and better in an acidic condition and a lower pH. And the sulfonates that we discussed earlier are acidic. So it depends on how you look at it from a science standpoint. Any other quick questions? Because I know we need to move forward, but we're having a break. And if you don't want to take a break, I'll stand here, or I'll stay here. I'm not going to stand, I'm going to sit and talk to you about any questions you may have.